All right, so now we've learned a little bit about invariant tests or fuzzing tests and why they are so absolutely crucial, especially for a project like this. So we're going to write some stateful fuzz tests or invariant tests in Foundry so we can have some more confidence that our code actually does what we want it to do. And the method that we saw in that video that we just watched is kind of the most basic methodology out there. And if we go to the Foundry docs, we can go on the left side, go all the way down to fuzz testing, or excuse me, go all the way down to this invariant testing, which invariant testing, like I said, is stateful fuzz testing. And we can read more about some of the more advanced ways to do these fuzz tests or these invariant tests. We're still going to do the target contracts, but what we saw in the video was a type of open testing, right? Where we just have function invariant A and then the assert. And what this does is it just calls all the functions on this contract to try to break that invariant. Now, this is good. This is great for an initial run of the code. However, we want to do for more advanced systems like ours, handler-based testing. Sufficiently complex protocols are going to have so many different random intricacies that we want to narrow down the random call so that we can have a higher likelihood of getting and catching actual errors. So we're going to do this handler-based type of testing. In this example here, in this open testing, it just calls any of the functions in the contract in any order. And handler-based testing, if we scroll down, we can kind of see this example here, where we create a contract called handler, where we only call functions in specific ways. For example, when depositing tokens, we need to make sure an approve happens beforehand. If you just call deposit without approving that token, that's kind of a wasted fuzz run. And if we only have 200 fuzz runs and we're wasting them on failed fuzz runs, well, the chance of us actually finding a bug becomes smaller. So if you think of the open fuzz testing like this, where you have Foundry, you call a whole bunch of functions on the protocol with the asserts. Handler is going to call functions in specific ways to the functions so that we have a higher likelihood of calling functions in orders that we want. So we're going to learn about this handler-based methodology, and we're going to build an incredibly verbose fuzz testing or invariant testing setup. Now, in our Foundry.toml, to work with these fuzz or these invariant tests, we can do this in variant section here. We can say the number of runs, we'll say is 128. We can also say the depth, which is the number of calls in a single run, which we might do 128. And then one of the most important keywords you're going to run into is this fail on revert. So let's talk about this fail on revert keyword and setting. So to create some invariant tests, let's create a new folder or fuzz test called fuzz or invariant or whatever you want to call it. And in here, we're going to need to actually create two different files. We're going to do invariance test.t.sol, and then handler.t.sol. This invariance file is going to have our invariance, aka our properties of the system that should always hold, right? That we just learned from that video. And this handler is going to narrow down the way that we call functions. This way, we don't waste runs, like I was saying. Again, if we call deposit collateral in our stablecoin without approving that stablecoin, that's kind of a wasted run, and we don't want to waste runs. So this handler is going to set our code up, set our contracts up so that we don't waste these runs. And we're going to come back to this fail and revert in a second. For now, let's actually set this to false, and we'll set it to true soon. But so the first thing we always want to do when writing invariant tests, when working with this, is want to ask the question, what are our invariants? What are the properties of the system that should always hold? Well, we can think of some, right? Well, one, the total supply of DSC should be less than the total value of collateral. Follow the word wrap. The total supply of DSC, which is essentially the debt, should always be less than the total value of collateral. Great, we have an invariant that we can test, and we should throw a ton of random function calls to try to break this one. Okay, what else? What other invariants should we have? Maybe our getter functions, our getter view functions, should never revert. And this is actually sort of an evergreen invariant. Most protocols can and should probably just have an invariant that looks like this. Getter view function should never revert. Now, we can probably think of more, but because doing these invariant tests can be a little bit time intensive, we're just going to focus on these two for now. These are going to be the two invariants that we focus on and we try to work with. So let's begin working and writing our invariant tests. And then we're also going to write our handler to help make sure all the function calls that we're working with actually do what we want them to do. Okay, let's do it. So this is going to be another test file. So spdx, license, identifier MIT, pragma. So, oh, well, that's nice. That kind of just automatically added it for me. Let's put this to the top. 0.8.18, a little caret here. Contract, invariance, test, like this. And to do this, we're going to say, we're going to have to import some stuff. We're going to import test from forge std/test.sol and import std in variant from forge std invariant dot sol. This contract invariant test. And then we're going to say this is std invariant and its test. So this std invariant contract, if we click into it, it has all this stuff that we're going to need to work with the invariants. One of the most important functions that it gives us is this target contract, where it says, hey, this is the contract I want you to call all these random functions on. Okay, great. Now, just like our normal tests, we're going to have a function setup, external, like this, and we're going to set up some stuff, right? A lot of this is going to look similar to our unit tests. So we're going to have to import deploy dsc from //script /deploy dsc.s.sol, import dsce engine from //src /dsc engine.sol, like this. And we'll say deploy dsc deployer equals new deploy dsc, and then of course dsc engine dsce equals deployer.run, and this actually returns a whole bunch of stuff: decentralized stablecoin, dsce, and helper config. So this is going to be, we also need a dsc, so we're going to import that. Import the centralized stablecoin from //src /decentralized stablecoin.sol. So we're going to do decentralized stablecoin dsc, and let's get the helper config as well. Import helper config from //script /helper config.s.sol helper config. Great. And so this returns the dsc, dsce, and config equals deployer.run. Great. And now, if we were doing this open testing methodology, right? If we go back to the docs here, if we're doing this open testing methodology, we could kind of finish this right now. So what we would do is we would say target contract address dsce, like this, paste this in here. And then just by adding this, we're telling Foundry, hey, go ahead, go wild on this, right? Go absolutely wild on this. And actually, let's even rename this. Call this open invariant test.t.sol. Open invariant test.t.sol. So we'll say absolutely go buck wild on this. And now we can add our invariant, right? We'll say function invariant underscore protocol must have more value than total supply. And this will be a view function. And what we can just say is we want to get the value of all the collateral in the protocol, compare it to all the debt or the DSC. So we can do that pretty easily by using the collaterals itself, right? Using our helper config, we'll say helper config.active network config. We can get the, well, what does this one do again? Let's open up the helper config. We can get these two tokens and just say, okay, well, what's the balance of these two tokens in our DSC engine? And then what's their value, right? So we'll just get those two tokens. So we're going to do nothing, with Bitcoin, nothing. So we'll do blank, with BTC, nothing. And then Those are ERC20s. So we'll import IERC20 from, all right, cool. That looks good. So we'll say ERC20 WETH, IERC20 BTC. This is wrapped BTC. Oops, sorry, this is config.active network config. We need to wrap this IERC20 like this. What am I messing up? Oh, let's just do address WETH then. Address WETH, address BTC, like this. All right, cool. So we're getting WETH in Bitcoin. There's going to be wrapped ETH and wrapped Bitcoin. And now what we can do is first we'll say uint 256 total supply equals DSC dot total supply. So this is the total supply of all DSC in the entire world, right? And we know the only way to mint DSC is through the DSC engine. So through people depositing and withdrawing collateral. Now what we can do is we can say, okay, let's get the uint 256 total WETH deposited equals, and this is where we can do IERC20 WETH dot balance of address DSC. So this is going to be the total amount of WETH deposited into that contract, or just the total amount of WETH sent to that contract. Then we're going to say uint 256 total BTC deposited equals IERC20 wrapped BTC dot balance of address DSC. So we have the total WETH, total Bitcoin. Now we can get those values. We can say uint 256 WETH value equals, we have a function here called get USD value, where we can get the USD value of any token of any amount. So we're just going to use that. WETH value is going to be DSCE dot get USD value, WETH, and the total WETH deposited, uint 256, wrapped BTC value, same thing, get USD value, wrapped BTC, total BTC deposited. And now what we can do is we can do assert the WETH value plus the wrapped Bitcoin value is greater than the total supply. And this is all we would need to do for this open testing, this open invariance. That's it. We're done. Boom. And this is why this is the easiest type of invariant test. But you'll see, running this, we won't get great results. So let's do forge test.m. And now what this is going to do is it's going to call all types of functions on our DSCE and try to break this invariant. So it looks like it was able to break this really easily. So let's clear this and we'll add our dash VV. We'll see what's up. Yep, assertion violated. We're having a hard time actually seeing the numbers. So we're going to import console in here. Test console. And we're just going to say console.log WETH value, semicolon, WETH value, or that's wrap BTC WETH, wrapped BTC value, console.log, total supply. Let's run this again. Now what do we get? Well, we got our first issue is that these are all zeros, right? And if they're all zeros, then this doesn't hold. So we can do greater than or equal to. This is kind of a bit of a cop-out, right? Because if they're equal, that makes us nervous, but it's fine, right? We should always at least have more collateral in the system than total supply. So now let's try again. Run this test again. Compiler runs successful. And we get, hey, you pass. There's no way for us to make it such that the total supply is lower. So this is awesome, right? Well, it's not that awesome. We didn't find any issues. We're looking to find issues. So maybe we need to bump up the number of runs. Maybe we need to bump it up to 1,000. And let's run this again. Now you're going to see this is going to take a lot longer. Because before it was doing 100 runs at 128 depth. Now it's doing 1,000 runs. And each one of these runs has 128. So it took a lot longer. And you can see that it took 14 seconds as opposed to what did it do before with 128. We run that. It did it in 1.5 seconds. But if we look up here on this line is incredibly important. we have calls, and we have reverts. So this made 16,384 calls and reverted 16,384 times. So basically, it wasn't even able to do anything, right? So what if we bump this up to 1,000? Clear, run this. We're gonna have to wait a few more seconds again. Ugh. So it did this many calls and it also reverted this many times. And the reason that this is still saying pass though, is because we have this fail on revert equals false. And this fail on revert equals false has some pros and it has some cons. The pro of fail on reverse equals false is that we can very quickly write open testing functions like this, and we can very quickly write minimal handler functions that aren't perfect. But the downside is it's hard for us to make sure that all the calls we're making actually make sense, right? Because this could be calling on our engine. Maybe it's just trying to deposit collateral, but it keeps using random collateral addresses that don't make any sense. So maybe it's calling this 128,000 times with 128 different collateral addresses, but only 2 work, right? So doing like this is cool for kind of some sanity check, and maybe it'll catch something, but it seems like it's not actually catching anything, right? And that's not a very good use of this. So revert on false is fantastic for quick tests. And often if I'm doing a competitive audit, which you can learn more about in the security course coming out soon, hopefully. If I'm doing competitive audit, a lot of times I will have revert on false be false, just so I can write up invariant tests quickly. I will also write handlers as well, like mini handlers, just so I don't have to get every nook and cranny, but I still will write a handler so I can narrow down some of the functions. But this open invariance seems to have this major flaw where it's probably making a bunch of silly calls. So this is great for very small contracts, but the more complex you get, like our system here, this open invariant system, it probably doesn't make sense for us to do because it's not going to catch anything. It's just going to keep breaking. Now, if we set this to true, we open this back up, we run this again, you'll see exactly one of the calls it makes that breaks. So it looks like it called redeem collateral for DSC. This is the first function call it made, which obviously doesn't make any sense because you can't redeem any collateral unless you have deposited collateral. And you can see the args it put in. It put in some random address, some random amount, a random amount, and then another random number, right? And you'll see we can call this many times and it'll keep giving us different places that it ran into issues. When we say revert on false is true, this can give us some peace of mind knowing that if this test passes, that means all of the transactions that went through actually went through and it didn't make a bunch of really dumb calls here, right? So here, fail on revert was false. We called liquidate first, which obviously doesn't make any sense with some horrible random address, some random amount, right? None of these make any sense. We call it again. We failed again. It called deposit collateral mint DSC, which is good. All right, so we're trying to deposit collateral, but it used some random address that isn't approved, some horrible amounts here, and it just keeps failing, right? So we want to try to prevent, and you can see here in the call summary, it made one run, one call, and that call reverted, right? So we want to narrow this down to try to point our fuzz, our random runs in a direction that makes a lot more sense, right? So this is cool, not great. Open invariance, I'm just now going to comment out this whole page because we're not going to use this anymore, okay? I'm going to leave the file in here though. We're going to create a new file though. We're going to call this invariance t.sol. I am going to copy this whole invariance thing, paste it in here and uncomment it. And we're going to level this up so that this invariance file, actually, let's just call this invariance, so that this new one is using this handler method. It's using this handler method to narrow down the function calls. And we'll do a mix of setting this to true and false, and you'll see where some of the advantages and disadvantages are.